Now, what we're doing today is we'll finish up 4.3, and I was originally planning on just doing 4.3 and then kind of being done for the day, but I realized that we have literally 2 sets of problems and then we're done with this note sheet. So we were almost finished yesterday. Now, what we have here is using transformations to graph these functions. Now, I did include this here. Inside the parentheses is our horizontal shift. We're either moving it left or right, a certain amount. And the K value is going to be up or down. And with most of these here, especially on Alex, these are going to be pretty easy to graph, especially with horizontal and vertical shift. Because if we look at this here, this function, we have plus 3 inside the parentheses, which means it's going to move the function 3 units to the left. But since it's plus 3, it's the opposite of what we think. It moves it 3 units to the left. And then our minus 2 is going to move it 2 units down. And for most of the homework problems like this on Alex, it's already going to give you the function itself. It's already going to give it to you graphed. You just have to grab the function and move it 3 units left and 2 units down. And the main point I would make sure that is moved that direction is the point here, 0, 1. Make sure, nope, because I'm thinking exponential. It's our 1, 0. Because when we talked about the graph for logarithmic, all of them are going to have this point 1, 0. They're going to have that point to start with as the basic logarithmic function. So log base 2 of x will have the point 1, 0. So we're going to take that point and move it 3 units left and 2 units down. So this here is the graph that they would start with, and we can see we do have that point 1, 0. But we're going to move it 3 units left, 2 units down. So that would mean that at the point -2, we should have a point -1 because we move it 3 units left, 2 units down. Or I can write this out. Because if we move it 3 units to the left, we're subtracting 3 from 1, which would give us -2, 0, 3 left. Then we move it 2 down, subtracting 2 from 0, which should give us the point -2, 2. And in the graphing calculator, I can say math log base 2 of x plus 3 minus 2. And we get this function here. And if we look at the graph, at -2, we have a y value of 2. We moved it left 3, down 2. And that would be it. Now, the vertical asymptote, the original one was x equals 0. However, we moved the entire function 3 units to the left. So the horizontal asymptote is also going to move 3 units to the left. So our vertical asymptote is now x equals -3. And the last thing we have is domain and range. Now the range is still going to be -∞ to infinity. All real numbers. Now, if we look at the domain, the graph of our red function here, we do see that it goes off to the right. So the biggest number that we can have is infinity. And the smallest number is going to be whatever the vertical asymptote is, so -3. If it had gone to the left, it would have been -infinity to -3 if we're graphing it to the left. But that's it. Now for these here, we're just writing the domain in interval notation. So we can look at the first one, log base 2 of 2x plus 4. So one thing that can be helpful is graphing it. And we get this here. Yep. Log base 2 of 2x plus 4. Now, if we look at the graph, we do see that we're going to the right. So for the domain, the biggest number we can have is infinity, because if it goes to the right, the biggest number is going to be infinity. Now we just need the vertical asymptote. And the vertical asymptote is really going to be the first spot we get an error occurring. So that would be -2. So the domain is from -2 to infinity. And that's it. And we could say the range, but the range for this here is still going to be all real numbers. Any questions on the first one before we look at the next one? ln of 5 minus x graph. Now, if we look at the domain for this one here, it's going to the left. So that tells us that the smallest number of the domain is going to be -infinity. Now we just need to figure out what the biggest value is going to be. Well, really the first one that gives us an error is 5. So here the biggest value that we're going to get is 5. And the real reason for either one of these here is because what's inside the logarithm cannot be 0 or negative, is where this is coming from. So if we look at the last one here, x squared minus 9. With any of these here, this cannot be 0. So we could, we'll do it in the calculator also, set it equal to 0. Add 9 to both sides. X squared is equal to 9. Square root both sides, telling us x is equal to plus or minus 3. So at these two values, we're going to have restrictions. Well, most likely that means we're going to have more than one part for this domain. And if we look at the function, we'll see this here. So we can say log of x squared minus 9. We have two different parts for this graph. Now, looking at the graph, we do go two different directions. So we are going to positive infinity and negative infinity. So in one of these, we're going to have negative infinity. The other, we're going to have positive infinity. Now, there are two spots where it stops. And if we look at the table, one of them is at -3, and the other is at 3. So for our domain, we're actually going to get negative infinity to negative 3, union 3 to infinity. And part of the reason for this is because what's inside here cannot be 0. And at 3 and negative 3, we do get a value of 0. However, if I pick a point between those two, I'm going to write the whole thing, log of negative 2 squared minus 9. Well, this would be log of, well, negative 2 squared is 4. But 4 minus 9 is negative 5. We can't have this inside the log. Now, that seems like a very odd stipulation to have. But part of the reason for this is if we go about solving this, put both sides to the 10th power, we're saying 10 to what power is a negative number? 10 to what power is a negative number? Well, if I put x as any value greater than 1, we get bigger values of 10. We're at 10, 100, it's going to go up positive. If x is between 0 and 1, we're talking about radicals, because 1/2 is the same as the square root, which is going to make 10 smaller, but it's not going to make it negative. There's no way for it to be negative. And if we say x is less than 0, x is a negative number. So we're just saying 10 to the negative x is equal to negative 5. Well, that's just the same as saying 1 over 10 to the x is equal to negative 5. That's still not going to make 10 be a negative number. It's just going to make it smaller and smaller. So you all see this here? So what's inside this here cannot be negative. And interestingly enough, it actually also can't be 0. Because if we set this up here, again, do the same thing, 10 to both sides, these would cancel, telling us 0 is equal to 10 to the x. Well, there's no way for me to multiply 10 by itself any number of times and somehow magically get 0. The only way we can get 0 is if we multiply a number by 0. So inside logs and natural logs, we can't have 0. And if we look back at the other ones, here, 5 minus 5 is 0. Anything bigger than 5 would cause this to be negative. Here at negative 2, negative 2 times 2 is negative 4. Negative 4 plus 4 is 0. So again, we have 0 in negatives. But that's it with this here. Questions on any of this? We good with this here so far? Yes. Okay. All right. So what we're looking at is properties of logarithms. Now, there's 3 main properties with logarithms. The first is the product property. If we have 2 things multiplied together inside of the logarithm, then we can rewrite it as those 2 things being added together. Well, there's 4 main properties. We have these 3 and then the change of base. So if we have 2 numbers multiplied together or 2 things multiplied together inside the log, we can split them apart. Or, and we'll do this some with solving, if I have 2 logs with the same bases being added together, we can put them back to being multiplied. What's inside is being multiplied. If we have 2 things being divided by, or divided inside the log, we can rewrite it as subtraction. Or if we have 2 things being subtracted, 2 logs with the same base being subtracted, we can rewrite it as division of what's inside the log. And lastly, our power property. We can move the exponent of what's inside the logarithm to the front. So we move the p to the front and make it p log base b of x. Now for expanding, I would go in this order. We would go power, so for expanding we would do, not power, product. Make sure, sorry. Back up. Quotient, and then product, and power last. Quotient, product, power, because we want to take anything that's being divided and split it with the subtraction. Then if there's anything multiplied together, we split it apart and then do power last. Now, we also can condense. And if we condense, the first one we're going to do is power. Second is going to be product. And that's going to be it. Because when we get to condensing, I'll explain it a little bit better why we don't have quotient. But it's dealing with the power property. Because if we do have something being subtracted, I find condensing is going to be easier to treat that negative as a power number in front of it and pull it up than it is to try to figure out what's going to be easier to do first with those, quotient or product. And sometimes if we have more than one thing being subtracted, it gets a little tricky. So when we look at this first one here, write the logarithm as a sum and simplify it as possible, and we'll go from here. Now these first two are just product. We don't have anything being divided, but I do have two things being multiplied together, which means I can rewrite this as a sum of each of those terms with the same base. So I can rewrite log base 2 of 8x as log base 2 of 8 plus log base 2 of x. Now we can actually simplify log base 2 of 8 because we can do it in the calculator. Math log base 2 of 8 is 3. So we can just say that this is 3 plus log base 2 of x. Questions on this here? ln works the exact same way. The natural log works the exact same way. So if I have more than one thing multiplied together inside the log, we can rewrite it as a sum of the natural log of each term. Questions on any of this here? Question on anything we've done so far? Because these aren't that bad, they're just a little funky in how they work. We're ready for the next two. Now the next two are division. Well, okay. Now, you might be wondering why I didn't take the natural log of 5 or even attempt that. Is I would pick the other calculator. ln of 5 is not a nice number. ln, for us to get nice numbers, we need e because it matches with the base. Here, 8, I'll write this off to the side, log base 2 of 8. Well, 8 is a perfect cube. 8's 2 to the third. According to the power rule, we can move the 3 up front, telling us that we have 3 log base 2 of 2. Log base 2 of 2 is 1. 3 times 1 is 3. That's how we get that there. Does that kind of make sense? So, looking at it, and sometimes I have a bad habit of doing this, is I just was able to see 8 has a base of 2, so we can simplify it. So I did not just pick it out of random, I just knew that this would simplify to 3. Or that it would simplify down. Does that make sense? And again, with some of these here, we can plug them in and check and make sure to see if they do or do not. Now looking at both of these here, log base 3 of c over d, nothing's going to simplify to a number, mainly because we don't have a number inside the parentheses. However, if we look at b, we do have 1,000, and it's just the common log. And the common log's base is 10, so there's a good chance the log of 1,000 will simplify. But before we get to it, we have log base 3 of c divided by d. Whenever we have two things being divided inside the log, we can rewrite it as the log of those two things being subtracted. And that's it. Now the other one we have is log of x over 1,000. Since we have two things being subtracted, we can say this is log of x minus log of 1,000. Now since the base and the number inside of it can be rewritten as the base to a power, we can actually simplify log of 1,000. Does anybody have a guess at what it's going to be? 3? It is. Log of 1,000 is indeed 3. So we have log of x minus 3. Questions on this here? Power rule. Well, we're going to have to use our rational exponent property with this here, because whenever we have radicals, we're going to need to replace it or change it to a fractional exponent. So for us here, the fifth root of x squared, the square term, our x, is going to go on top of the fraction. The root is going to go on bottom. So the natural log of the fifth root of x squared is going to be the same as the natural log of x to the 5, or x to the 2/5. And according to our power property, we can move the 2/5 out front, telling us this is the same as 2/5 times the natural log of x. Yes. Now these here seem like they're a little challenging, this one here specifically, on making sure we get the correct answer. Now I can't plug it in. I can't plug in the natural log of x into the calculator and get a number. It will give me a number, but I've got to put values in and we can check it. However, a way kind of around that, let's put 5 math x squared. If I type this in and hit graph, we get the graph of the function, yes? Now what I can do, just to kind of check it, is say alpha y equals enter. So what we found in a simplified form was 2/5 ln of x, yes? These should be the same function. So if I graphed it, the red graph should cover up the blue graph. And it does for the most part. It's just the other side doesn't work out. But that's mainly dealing to the fact that the x is not squared anymore, so we don't get the positive negative. But this is the simplified version of it. Questions on this here? B, log of x squared. Well, this one's a little bit nicer. We don't have to do any simplifying. We can just move the exponent to the front, telling us that it's 2 log of x. Any questions on this here? Now, before we get into these here, we're going to actually pick this up tomorrow. I'm not going to go all the way to the bell today. Since we did 2 of these, I'm going to stop